Yeah. So let me share my screen. Yeah. I hope my presentation is visible and I am audible. And let's see. Oh. So welcome you all to the week 2 live interaction session for this course Bioelectrochemistry. This course is offered by Professor Mainak Das from the Department of Biological Sciences and Bioengineering from IIT Kanpur under the NPTEL program. Myself Pratyumnan, a PhD student, Department of Chemical Engineering at IIT Guwahati. I am one of the course team members responsible for conducting the live interaction session every week. So, in the very first live interaction session, we covered on the basics and fundamentals of the electrochemistry part. So, our journey in this electrochemistry or understanding the fundamentals of the electrochemistry will continue even in week 2 before we really progress to deal how this electrochemistry is being used for the biological applications. So, if you remember, in the last class we discussed about very basic fundamentals of electrochemistry, starting from what is current, and how do you define current, how do you define voltage, how do you define power, and also we discussed on some of the concepts, or you can say the galvanic cell, the most popular galvanic cell we discussed, which is nothing but it's your zinc copper Daniel cell. So here we talked about how, here we talked in detail about the architecture of the galvanic cell. So where we use zinc in zinc sulfate electrolyte as one compartment separated using a porous disc, and in the second compartment you have the copper electrode in copper sulfate. So both this compartment are separated using a porous disc. Now here we discussed in detail about what kind of reactions takes place, how the redox reaction takes place at the anode and the cathode, and how overall the electrical neutrality in the system is maintained. So in all the electrochemical cells that we usually discuss, or that is taken for taken for study, the main principle that we need to keep in our mind, or that we need to actually remember, is that the neutrality, or you can, to be very specific, the electrical neutrality should be maintained. Charge neutrality should always be maintained. So there cannot be a system wherein you can have excess of positive charge or excess of negative charge, or deficiency of positive charge and deficiency of negative charges. The electrical neutrality within the system has to be maintained, so that remains one of the most important condition for the operation of any kind of electrochemical cell that you're going to study, or that you're going to examine, or that you're going to construct. So that is a very important point, so that I will be specifically mentioning it here. Electrical neutrality has to be maintained, needs to be maintained. And in order to maintain this electrical neutrality, we usually manipulate the architecture of the electrochemical cell in such a way that it does not disturb the electrochemical reactions that is happening in the system, but at the same time make sure that the charge do not get built up in any particular compartment. So that's how last time we discussed how the let me just to go back, that in case of the anodic compartment, we had more amount of the SO2 minus ions, which are where we had more amount of zinc 2 plus ions, which is usually released into the electrolyte. And how to maintain the neutrality of the system, the SO2 minus ions move from the cathodic compartment to anodic compartment and neutralizes the charge in the anodic compartment. Similarly, the electrons move from the anode to the cathode, and then the Cu2 plus ions along with the two electrons undergo reduction, leading to the formation of the copper, which gets deposited on the surface of the electrode. And we also discussed about the typical representation of a galvanic cell. So this is the typical representation of a electrochemical cell. So where you first write the electrochemical reaction that happen in an anodic compartment of a cell separate, and then you have the interface that separates both the compartment, and then you basically write the reactions or the electrochemical reactions that happen in the cathodic compartment. So this is the typical convention for writing the electrochemical reactions or for representing the electrochemical cell. So apart from this galvanic cell, or you can say the zinc copper cell, there are also two more types of electrochemical cells were discussed. One thing is the cadmium and silver electrode dipped in cadmium chloride solution, and another one is the cadmium electrode and silver electrode dipped in a mixture of electrolytes, that is nothing but the cadmium nitrate and silver nitrate. So there was a problem in the mixture of electrolyte. So I hope all of you know what is actually the problem that's happening in that particular system, in that particular electrochemical system. Anyone? Here there was a porous disc. In case of a zinc copper system, you had a porous disc which actually separates both the compartment, kind of form an interface between the compartment. In the next case, we usually saw a mixture of electrolyte between the cadmium nitrate and silver nitrate. However, there was a problem that the amount of current that got generated through this electrochemical reaction was not sufficient enough. So the question is why this particular issue is happening in those kind of systems. Yes, anyone? I think this we discussed in the last class, and even in the course content, this particular um, what do you say concept is discussed once again. Why is that? In case of a mixture of electrolyte, when we take cadmium nitrate plus silver nitrate, the electric current that gets generated or the amount of potential that you derive from that electrochemical cell is usually very less. Anyone? Okay, so typically there is a reason on why the what do you say the electric current that gets generated, or the electric current that is generated in those cases with the mixture of electrolyte is not sufficient enough. So that is the question. I hope answers. If anyone here knows, then they can tell, or or have a look at it, because this is, it's directly there in the course contents. Because keeping this as a point is where we actually move to the concept of salt bridge. It's quite simple. So in case of a mixture of electrolyte of cadmium nitrate and silver nitrate, you are going to have two types of cations on the surface. So the cadmium side, the cadmium electrode, is the anode, so where the oxidation takes place. So the cadmium forms Cd2 plus 2 and releases 2 electrons. That Cd2 plus gets inside the aqueous electrolyte. This Cd gets into the aqueous electrolyte. The silver nitrate solution, instead of accepting the electron from the anodic side and then getting deposited on the surface of the silver electrode, it gets more preferentially adsorbed to the cadmium surface. So the Ag plus gets attracted more to the cadmium surface, due to which the reduction reactions does not happen completely. So that typically becomes a reason. So there is a difficulty in the reduction of the Ag plus to form silver, or Ag plus to undergo reduction to deposit as a silver on the silver electrode. So typically due to this reason only, the amount of current that you actually want to derive from the system becomes a difficult task, or becomes a little bit tricky. So in order to minimize this problem, or basically to solve this problem, we come here with the concept of salt bridge. So the name itself is kind of a self-explanatory. It's like you use some sort of a salt and kind of make a bridge, which, so bridge here as such, in case of an electrochemical cell, we usually have anodic and cathodic compartment. So in relevant to this context, salt bridge is something that is going to use some sort of a salt and bridge both the anode as well as the cathodic compartment of the cell. So same system of the cadmium and the silver electrode. Here, instead of having a mixture of the electrolytes, we are going to separate them into two different compartments, but connect these two compartments using a salt bridge. So salt bridge is the concept. So typical explanation goes on like this. Salt is used to bridge the compartments of the electrochemical cell. So now in this case, you will have one particular compartment where you will have cadmium in cadmium nitrate electrolyte solution, and in another compartment you will have silver electrode in silver nitrate solution. So again, anode and cathode, so your cadmium will act as an anode and silver will act as a cathode, and then the each one of them will in each one of them the electrochemical reactions is going to happen. In case of the anode it is oxidation, in case of the cathode it is going to be the reduction. So if you write, then can anyone tell me what will be the reaction in the anodic side, oxidation? So cadmium is going to form cadmium 2 plus, and then donate, or you can say release, 2 electrons. And in case of your, and this is going to happen in the anode, and in case of your cathode the reduction is going to happen. So where the Ag plus, Ag with a single positive charge, sorry, 2 Ag plus will accept those 2 electrons that it receives, and undergo reduction to form 2 Ag. And this, oh sorry, and this Ag gets deposited on the surface of the silver electrode that is there in the cathodic compartment. So this is the typical concept of the of the galvanic cell. Now here, since there was a previously this problem wherein in case if you have a mixture of electrolyte, there was a problem in difficulty in there was a problem wherein we found that it was difficult for the Ag plus ions to undergo reduction. So we basically separated the compartments. So now problem is, in case of the anodic compartment, Cd2 plus ions are going to go inside the electrolyte, but you do not have sufficient amount of NO3 minus ions to maintain the charge neutrality in the anodic compartment. Similarly, in the cathodic compartment, the silver is going to be reduced to deposit as a solid silver. So the nitrate ion concentration in the cathodic compartment is going to increase. So the negative charge in the cathodic compartment is going to get increased. So charge neutrality is going to be compromised, which cannot be possible. So in order to make sure that this charge neutrality is maintained, we use a salt bridge. So this salt bridge is usually a U-shaped tube which is filled with a gel. So what is the gel like? Any kind of very commonly used concentration, very commonly used gel in case of salt bridge? Anyone? What is the commonly used salt bridge, the composition? So it's a U tube, and it's a U-shaped tube which is filled with a gel. So what is that gel which is most commonly used for salt bridge? Anyone? What is the composition of that gel that is used in the salt bridge? So it is 3 gram of agar in 30 gram of KCl in water. This KCl can also be replaced with the potassium nitrate. So in case of the cadmium silver electrode that we are discussing here, we use KNO3 for our salt bridge. So this gel will be filled inside the will be filled inside a U-shaped tube, and this U-shaped tube will be is the one that is going to connect both the anodic and the cathodic compartment. Here the concentration of the nitric of the potassium nitrate that we are going to use is going to be very high in comparison to the concentration of the salt that you have in the electrolyte in either of your anodic and cathodic compartment. So my question is, why is what is the need that, or why is that the concentration of the potassium nitrate in the salt bridge, it needs to be very high in comparison to the salt concentration in the anodic or the cathodic compartment. I can write this way. Concentration of salt in salt bridge is very high compared to the concentration of salt in the half cells. So why is that, why such a concentration gradient, or you can say why is such a condition, or is there is a requirement like this in case of an electrochemical cell? Why, what is the need for the concentration of the salt in the salt bridge to be excessively high in comparison to the salt concentration in either of the half cells, or you can say in the anode or cathode compartment? Yes, anyone? Why, what will happen if if I'm going to keep a salt bridge which has concentration that is something very similar or equal to or even less than the concentration of the salt in each of the half cells? To reduce the resistance and increase the current flow. Hmm. Okay, but can you explain why, I mean, or like how that actually, how that the if this concentration difference or this high concentration will help in doing that? Because if it is, if you're going to say that it is typically to reduce the resistance or the current flow, can you explain how, like how it does that? See how it is going to help as we progress through our discussion. Yes, it is correct that it basically helps to reduce the resistance and increase the current flow, because when you are going to use a high concentration gel electrolyte, what actually happens is it kind of provides a conductive pathway for the system. So that is one of the advantages of using a high concentration salt. But apart from that, you can also think from the perspective of what I just said now. For an electrochemical cell to function properly, this has to be a particular condition needs to be maintained. So if you think from that perspective, then that also forms as an answer for why the concentration of the salt needs to be high in case of the salt bridge. Okay, let's see why is that so. So as I said, in case of the anodic compartment, the Cd2 plus ions is going to be less, so nitrate ion is going to be more. NO3 minus is going to be more, and in this case, oh sorry, so cadmium 2 plus will actually go inside the electrolyte. So Cd2 plus is going to be more and NO3 minus is going to be less. Cd2 plus is more, and in this case NO3 minus is more. So in order to maintain the charge neutrality, in case of the anodic side, then NO3 minus ions will actually move out, or it will move from the salt bridge to the anodic compartment, and some amount of the Cd2 plus will enter from the anodic compartment electrolyte to the salt bridge. Similarly, in order to reduce the negative charge that gets built up in the cathodic compartment, K plus ions will move out from the salt bridge to the electrolyte. At the same time, some amount of the NO3 minus ions will move from the electrolyte to the salt bridge. So if you see overall, the charge neutrality within the system will be maintained. So let me write this so that the things are more clear. Cd2 plus is more in let me just write that way. In anode, Cd2 plus is more. So NO3 minus ions from the salt bridge diffuses to the electrolyte. And in case of cathode, NO3 minus ions is more, So K plus ions from the salt bridge diffuses to the electrolyte. So since so if you see so here, apart from that, the some amount of the Cd2 plus will also be entering inside the uh, salt bridge, so that the charge neutrality within the salt bridge get maintained. At the same time, even in the cathodic compartment, some amount of the nitrate ions will move from the cathode to the sorry, from the electrolyte in the cathode to the salt bridge, so that if you take each and every system individually, their charge neutrality is maintained. Only the main particular reason for using the salt bridge is to make sure that there is no charge offsets, or offsets in the charge is minimized. The charge neutrality in each and every compartment of an electrochemical cell needs to be maintained, and overall, if you see, for the electrochemical cell, their charge neutrality must be maintained. For that particular purpose, we go for using the salt bridge, so that we can maintain this charge neutrality or electrical neutrality in the system. And that's why the concentration of the salt bridge also needs to be excessively very high, because in order to maintain the neutrality in the system, more amount of the ions are actually required to be diffused into either of the electrolytes. So if you're going to have some sort of less concentration, or a very dilute salt concentration within the salt bridge, then those will not be sufficient enough to maintain the charge neutrality, or those will not be sufficient enough to bring down the offsets in the charges created during the electrochemical redox reactions. So that is one of the reasons why the concentration of the salt in the salt bridge needs to be high. Second reason, as one of you rightly said, that by using a high concentration of salt, you basically reduce the internal resistance that gets built up within the system, and by using a high concentration of the salt, you basically provide a more conductive pathway, which provides an enhanced electron or charge flow, leading to increased current flow, so more amount of the energy can be harnessed from the electrochemical system. So these are the 2 points for why they for why the concentration of the salt in the salt bridge is going to be high. So I'll write those: to maintain charge neutrality, and second thing is to reduce internal resistance and increase current flow in the electrochemical cell. So these are the two reasons for why the concentration of the salt bridge in the should be needs to be much greater compared to the concentration of the salt in each of the half cells. So this is about the typical use of salt bridge concept. Next, we actually move on towards the concept of SHE, standard hydrogen electrode. So here we use hydrogen as a standard, and based on that we actually measure the potential values for the other elements, their oxidation and reduction potential values for the other elements. So the standard hydrogen electrode is typically used as a reference electrode to actually measure the half cell reaction potentials. And And the standard hydrogen electrode is nothing but you have a, so the construction is typically like this. Let, I think, is it possible to describe that here? Yeah. Standard hydrogen electrode. So, in order to typically measure this, or you can say in order to, so based on this standard hydrogen, so using this standard hydrogen electrode, we basically measure the standard potential. So here what we actually do is we take a finely divided platinum electrode, finely divided. Again, everything is covered by professor. This is, as I usually say, this is just a recap or a review of what we have done previous, of what is done in the course in that particular week. Finely divided the platinum electrode surface, and to this electrode you actually purge hydrogen gas at 1 atm pressure, and this electrode is immersed in HCl solution. So what happens is the hydrogen gas reacts on the platinum surface, undergoes the reduction reaction to form solid hydrogen on the platinum surface. So the reaction is something like this. Gives 2H plus 2 electrons. Again, this is a reversible one, so I need to be careful when I write this. So, oh, yeah, I think this is correct. So again, I will modify all the notations while uploading the presentation. So since this is an online session and such things take time, so let the so for the time being, kindly adjust. But all the notations will be proper. So all the notations will be corrected once the final PPT is uploaded into the portal. So this is the reduction reaction of the hydrogen gas that happens on the platinum surface. Hydrogen gas undergoes reduction to form or to release two H plus ions plus two electrodes. These two H plus ions get adsorbed onto the surface of the platinum electrode. So the E, that is the voltage of this particular reaction, is given out to be 0 volt. So based on this, we are actually going to measure the potential of the other elements. So whether they are going to be metals, for different kind of metals, what will be the reduction or the oxidation potential, that will be decided by using this hydrogen as a reference. So now here I actually want to know, I mean, if you guys have any idea, or while listening to the, or while learning from the course, did you ever think about why is hydrogen taken as a reference? Why can't I use some other material as a reference for studying this electrochemical studies? Anyone? Any thoughts on why hydrogen is used? Why not some other? I mean, the periodic table is densely populated with so many elements, but why hydrogen is used as a standard to study the or to measure the reduction potential or oxidation potential of other elements. Before asking this, I want to ask one more question. Why is platinum electrode used in this is used in this experiment to measure the standard potential or of to measure the standard potential? Why is platinum electrode used? Why not some other electrode? Because platinum is quite expensive, right? And it is going to be in a solution of of HCl, which is having a concentration of 1 molarity. 1 molar HCl solution, the platinum electrode is going to be dipped, and then you pass the hydrogen gas at one atmospheric pressure, and then the reduction reaction takes place, leading to the um, H plus ions being deposited on the platinum surface. They are adsorbed onto the platinum surface as a solid hydrogen. So why is platinum electrode is used? So two questions: why is platinum electrode, and why hydrogen is kept as a standard reference for measuring the oxidation or reduction potential of other elements. Yes, anyone? Why is platinum electrode used? Why not some other materials, let's say copper, or you can say zinc, zinc electrodes? Why is platinum electrode is used as a why is platinum used as an electrode in this to measure this standard potential? Platinum is highly inert in nature, that's true. Yes, that is absolutely correct, because so the inert nature of the platinum is what it makes it kind of universally used in multiple electrode systems, because platinum remains inert to multiple acid solutions as well, high concentration acid solutions. And the for the next question, H2 has zero potential. Yes, so that is the reason why hydrogen is used as a, actually that is kind of the zero potential is, it's not its absolute potential value, that is the relative potential. So here in today's session we will today's or probably in the next live interaction session we will actually solve one problem where the absolute value of the standard hydrogen electrode or the absolute potential value of SHE is not zero. It's a different value, that stating that that the potential of SHE is 0, it is the relative potential value. So think about this on why hydrogen is used as a standard reference. I will place this question. Is used as a standard. I'm going to keep. Let me color code this into different. So think on this, because as I said, the absolute potential for the SHE is not 0. That is the relative potential for SHE. Think about this, because okay, think about this. Let's discuss on this once you have some ideas related to this. Next comes the electrochemical series. So in the last session, I hope I remember, or I asked some of you, I mean all of you here, to actually go and have a look at the electrochemical series. And I also asked, why is all the standard potentials usually represented in the form of, usually is reduction potentials? Why not oxidation potentials? So this is the electrochemical series. Let me just. So you have series of elements starting from lithium, potassium, calcium, sodium, magnesium till fluorine, and on the right hand side you have the standard potential V. So for lithium it is just a second, I will just move this. Okay. Now I think it will be fine. So for lithium it will be -3, and for potassium it is -2. And remember, all these are standard reduction potential values. To answer the last class question on why you cannot represent them in terms of oxidation potentials, you can absolutely represent them in terms of oxidation potentials. However, the magnitude will remain the same, but the sign will change. So be careful, and once you start representing a particular element in terms of its oxidation potential, or you speak about a particular element's oxidation potential, then when you compare them with the other elements, make sure that you maintain your comparison both in terms of the same oxidation potentials or reduction potentials. So it should not happen that you are going to consider the reduction potential of lithium and compare it with the oxidation potential of, let's say, cadmium. So that uniformity has to be maintained. So in order to make sure that such confusion do not arises, as a standard convention, in most of the cases, if you see, people, or you can say scientists, use standard reduction potential values for the calculations. If you are okay with this, then go ahead, or in case if you want to use oxidation potential values, then it's absolutely fine, there is nothing wrong. But be careful with the values, especially when I say values, I mean the sign, whether it is positive or negative. And in comparing two elements, so starting from lithium you have till fluorium, you have till fluorine. So apart from this, for other elements also you have the half cell reaction. This is not an exhaustive list, so you're welcome to Google up for a more exhaustive list on the different types of elements, their half cell reactions, and their standard reduction potential values. So what does So let me put forward a question. What does this reduction potential values actually tells you? I mean, again, the picture is self-explanatory, but again, I want any one of you to let me know what you can actually infer from this electrochemical series. Yes, these are the standard reduction potential values, and you can also see the related words on weaker oxidation agent, and at the bottom it is written stronger oxidation agent and others. So, what it actually means? What do you actually infer from these values? Yes, I this should not be quite difficult. So, what is the meaning of oxidizing and reducing agent? If you know that properly, then this values should tell you what it actually means. It typically determines the fact that how far it is easy or difficult for a particular element to either gain or donate an electron. So having a larger negative potential values or larger negative reduction potential values typically represent for the fact that it is difficult for them to undergo reduction. So if you see in case of lithium and potassium, for them to accept an electron to and then move to its elemental state is going to be very difficult in comparison to, let's say, chlorine or gold. They tend to accept electron and then move towards their elemental state. That will be far easier for them. So using this reduction potential values, you can actually tell that if the standard reduction potential values is going to be very negative or largely negative, then it typically means that the elements find it difficult to undergo reduction and are more preferable to donate the electrons and undergo oxidation. Whereas if the values are going to be largely positive, then it typically represents that they can easily undergo reduction, but for them to donate an electron, it will be difficult. So that's what is written, weaker oxidizing agent. So that typically represents that it cannot oxidize the other material and cannot reduce itself. That's what I hope we learned last time, right? What is the definition for oxidizing agent and reducing agent? Because this particular electrochemical series will be very useful when you learn about the concept of Nernst equation. So in Nernst equation, when you try to calculate the EMF, electromotive force, or you can say the potential or voltage of a cell, you need to know these values. They will become a, become critical when while we solve problems today towards the within the next 5 minutes or so. So if you have any doubts related to this electrochemical series, please let me know. Before we move to the Nernst equation, again, Nernst equation is nothing much. It's just about how to calculate the EMF of a half cell. So I hope there are not much queries related to this electrochemical series. So let's move to Nernst equation. So Nernst equation usually helps us in determining the EMF of a particular half cell reaction. So that is what is typically represented in this equation. So if A accepts electron to and then transforms into B, then the E or the voltage of this particular reaction can be represented as E equals to E naught minus RT by NF, ln of concentration of B to the power B by concentration of A to the power A, or you can also represent it in terms of activity coefficients. So it is typically not correct to write this as E cell. So I'm going to, this will be fine. So we end our concept discussions here. If you have any doubts, please let me know, because this electrochemical series specifically is very important, because people usually make mistakes while calculating the EMF of the cell. So it is important that a good understanding is there for on this electrochemical series. So if you have anything to ask, then please let me know. Is anyone with any queries? Okay, so let me just open up the questions. If you have any doubts, you are welcome to ask me, or you can go through them. So let me just read out the question. Salt concentration in the salt bridge is going to be dash than in the half cells. This we discuss right now. So this, you can either unmute yourself to reply to the answer, or if you have any question, or you can post your answer in the chat box. So for the first question, the answer is simple. We discuss right now. So this is going to be higher. So next question is, which of the following is not true about SHE? It uses a platinum electrode. Hydrogen is bubbled at a pressure of 1 mmHg. Concentration of H plus ions is equal to 1. 1 in the sense 1 molar. And last one is none of the above. Yeah, this should not be difficult. Which one of the following is not true about SHE? Just now we discussed about the operating conditions for SHE. Is it none of the above? Is the answer none of the above? Okay, one person says none of the above. So, is it okay with others? I feel the answer should be none of the above, but is it okay with others? What about option B? What should be the pressure range for bubbling this hydrogen inside the platinum electrode or inside this cell? 1 atm, okay, 1 atmosphere pressure. But here it says it is 1 mm of Hg, 1 mm of mercury. So, how much is how many mm of Hg makes up 1 atmosphere? Any idea on this? How many, 1 atmosphere is how many millimeters of mercury? It is 760. 760 mm of Hg makes up 1 atmosphere. So the correct answer for this is not D, but it is B. So here they are the question that they are asking is, which of the following is not going to be true about SHE? So option B, hydrogen is bubbled at a pressure of 1 mm of Hg is not true about the standard hydrogen electrode. Now let's come to question 3. For a balanced reaction for the standard hydrogen electrode SHE with 1 mole of hydrogen gas, how many moles of electrons are released? We wrote the reaction just now, so this is a very direct question. So this is the reaction, right? H2 gives 2 H plus plus 2 electrons. So for 1 mole of H2 gas that is going to be purged inside the platinum that is going to be purged through the platinum electrode surface, 2 moles of electrons will be released. So option C. Let's start solving the problem. So let's start with this one. Or let's start with a simple one. Question 7. Explain whether we can store copper sulfate in a nickel vessel or not. Let us keep the question 4, 5, and 6. We will come back to that. Let's start with numerical problem solving. So, I think that will probably involve a lot more participation from everyone. Can you store copper sulfate in nickel vessels? So read the question carefully and then using the values, the reduction potential values, tell me whether it is possible for storing copper sulfate in a nickel vessel. Are any thought ideas on how to solve this problem? This is actually quite an interesting question. That is the reason I took up this first in problems. Others, if you know the Nernst equation, you can solve. So this actually does not require Nernst equation, but you need to calculate the potential of the entire cell. Assume that copper sulfate in nickel vessel is kind of an electrochemical cell, and then calculate the potential for that cell. Then once you do that, you will be able to understand whether that will whether you can store it or not. Okay, let me give out the reaction first. Then you tell me whether this reaction is possible or not. So it says that can you store copper sulfate solution in a nickel vessel? So it should be something like this. So question is whether this reaction will happen or not. Now it's up to you to tell me whether this particular reaction is going to happen or not. Yes. So what is typically happening here? Nickel is getting oxidized and copper is getting reduced. Is that right? So this reaction, instead of playing with the sulfate, can I write nickel Is this correct? And copper, 2 plus, plus 2 electrons is going to form copper. So again, here it is said that it's a copper sulfate solution. So CuSO4 will exist in the form of Cu2 plus and SO4 2 minus ions. So this will be the reaction as per the equation that I have given. My question is whether this will happen or not is something that I do not know. So we are supposed to provide an understanding on, or we are supposed to gain an understanding on whether this reaction will happen, will progress or not. So we have a equation to calculate the EMF of a cell. E cell is nothing but it is E cathode minus E anode. This was discussed in the course lectures also. So it is, so since we are doing all this under standard conditions, so we can write this as E naught of cell, or I will just this should be actually E naught, or I'll write under standard condition. So now you know what is E anode. I mean, what is anode, and E anode is known. E cathode and E cathode is known. So can you calculate the voltage of the cell, or the voltage of the cell, or the EMF of the cell? Based on that value, you can easily tell whether I can go for this experiment on storing copper sulfate in a nickel solution or not, or the value of each cell, or some. Standard reduction potential values are given. So that is the values of cathode and anode. So based on this, you should be able to calculate the E of the cell. What is the EMF of the cell? Assume that this is an electrochemical cell, and then do the reactions, I mean, and then solve the problem. So E cathode, which is your cathode? Your cathode is Cu2 plus accepting 2 electrons to form copper. So that value is 0.34, and here everything is in terms of the reduction potential values. You can see nickel 2 plus 2 electrons gives nickel, and the reduction potential value is minus 2.5 volt. Copper accepting 2 electrons to form copper 0, or elemental copper, has a reduction potential value of 0.34, and you can also check it in the table. So nickel 2 plus is minus 0.25, and for copper it is 0.34. So you cannot, the major reason why I wanted to show that was you cannot take any arbitrary values for calculating the standard reduction potential. So those values need to be checked. So E cathode is minus 0.34 and E anode is, so even if I cannot give you any random reduction potential values here, so that actually goes against science. So that is one of the reason why I showed the electrochemical, the values in the electrochemical series. So minus E anode, E anode is nothing but it is your nickel whose value is minus 0.25. So this can be represented as 0.34 plus 0.25. Let me make it big. So which is nothing but 0.59 voltage. EMF of the cell is going to be a positive value, that is 0.59. So what it represents, this we saw in the last class. For a redox reaction or a chemical reaction to be spontaneous, the Gibbs free energy or the free energy of a chemical reaction needs to be negative. Then if that is true, then what will be the EMF of the cell? It should be positive, because delta G equals minus NFE, where N is the number of moles of electrons participating in the redox reaction, F is the Faraday's constant, and E is the EMF of the cell. If delta G is going to be negative for a spontaneous process, then minus NFE is also going to be negative. So which means that NFE, the value, it should be positive. So E should be positive. So I hope you remember this. So delta G is minus NFE. For a spontaneous process, this value should be less than 0. So which means that NFE should be greater than 0. That N and F, that is the number of moles of electrons participating in the redox reaction, and the Faraday's constant cannot be negative. So all the three so if out of three quantities, two quantities are positive, and all the and the product of all the three quantities should also be positive, then it means that the third quantity should also be positive. So E of the cell is positive. So that means that the reaction is going to happen. The reaction is spontaneous. It's going to happen, or it is likely to happen. So here E of the cell, EMF of the cell, or this particular reaction is positive. So which means that this reaction will happen. So whether it is ideal? No, because I cannot store copper sulfate in a nickel vessel, because after some time the nickel will not remain as nickel, it will form nickel sulfate, and the copper will get reduced to form elemental copper. The copper sulfate will reduce to form elemental copper. So not feasible. Reaction is feasible, hence copper sulfate cannot be stored in nickel vessel. Instead of saying reaction is feasible, I am going to write reaction is spontaneous. Hence, copper sulfate solution cannot be stored in nickel vessel. So, anything that you were not able to understand, please let me know, because this is quite simple one. So we will have problem using the Nernst equation, which is going to be a little bit, I mean, more tedious with calculations. So please let me know if you have anything that you were not able to understand here before we go for the other questions. Anyone? So if you do not have, or okay, let me just wait for a minute before I go further for the next questions. So let me just show you the next question. Okay, let us solve question 9 first before moving to 8. What is the number of electrons that gets transferred in an equation if the Nernst equation is E cell equals to E naught cell minus 7.375 into 10 power minus 3 times log 10 anode by cathode? Assume standard conditions. So this question, take temperature as 298 Kelvin, R value as 8.314, F as the Faraday's constant 96500. So based on that, solve and let me know what is the value of N. Okay, let me do one thing. Let me give you the expression here. Just compare the equation in the question with the equation that I have given and then calculate the value of N. T is 298 Kelvin and R is 8.314 joules per Kelvin. R is nothing but a universal gas constant. F is Faraday's constant, which value 95600 coulomb. You have to calculate the value of N. Once if we finish, we will go to question 8. Question number 7, I will give it to you as a kind of, you can practice at home. This is a big question, so solve this question, because once you solve this question, you will be having a practice. So these questions are much simpler version of the question 7. So I'm first dealing with the simple ones before we move on. So try to solve this in the week, I mean during the weekdays, and we can discuss that particular one in week 3 live interaction session. So now question 9 and 8. Value of N. Just a second. It's just that you need to write the value of RT by NF as 7.375 into 10 to the power minus 3. I mean, just equate both, and since I have already told the values, it's under the standard condition. So use R, T, and F values as such, and then get the value of N. So what will be the N value? Anyone has calculated? So, uh, so RT by NF is equal to 7.37, sorry, into 10 to the power minus 3. So we are supposed to calculate the value of n. So that will be nothing but RT by F times 7.375 times 10 to the power minus 3. So value of n will be nothing but R is 8.314. T, as I said, standard conditions 298 by Faraday's constant 95600 times the value 7.375 times 10 to the power minus 3. But here there is a catch. The expression what we have given is in terms of ln, but what is expressed in terms of the question is log. So you need to do the log to ln conversion, because in the question it is log to the base 10 and ln is log to the base e. So if you do that conversion, then you have to multiply an additional factor of 2.303. So if you solve for this, then what's the value of n? Let me also calculate side by side. Just calculate this value and then let me know. So let me calculate on 8.314 times 298 times 2.303 divided by 95600 times 7.375 times 0.001 There's some issue. Let me just write this way: 5705.6 by divided by 9560. 705.5. 5705.6 by 705.5. 8.08 again. If you take again, since the Faraday's exact value is 94, so there is a small change, so 8. Is there anything that you guys are not able to understand in this question? Then please let me know. Because if this is, because this is not a very difficult one. This is a very I mean, you just need to compare it and then let me know the value of n. So any doubts on this question? And I have specifically made a mistake in this question answer. So at least can anyone tell me what mistake I have committed? Because after this we will deal with a few numericals and then I'll close the session by 7:15. It's the value of the Faraday's constant. I wantedly took the value as 95600. Faraday's constant value is 96500. Somebody has written NS. Okay. 111.1. So I think that will make up the answer. 8. N is 8. So as someone has said, the value of n, the number of electrons or moles of electrons transferred as per this Nernst equation is 8. So let's go with these two questions. Question number 4 and 5 and 6. Three questions. Which of the following is not true to choose an electrode on which the redox reaction occurs for standard hydrogen electrode? It should be extremely reactive. It should be able to act as a catalyst for the cation reduction reaction. It should allow in reproducing the potential generated. It should have a high intrinsic exchange current density for reducing the protons. They're asking which is a false statement among the four. So C is correct. It should allow in reproducing the potential generated. And B is also correct. It should be able to act as a catalyst for the cation reduction reaction. D, it should have a high intrinsic exchange current density for reducing the proton is also correct, because the protons needs to be absorbed on the to the electrode surface. So option A is not correct. If it is going to be extremely reactive, then hydrogen will react with that element to form some other compound, so then it will not be useful, right? So it should not be extremely reactive. Then next question is, that's a simple one, I think fifth one. In an experiment, two exactly same galvanic cell, same operating condition, similar standards were used. One is having a salt bridge and then the other one without the salt bridge. Voltage output is same at the initial time points. Initially, when they measure the voltage from both the cell 1 and cell 2 with bridge and without the bridge, the voltage output is the same. Which one will function for longer time? The one with the salt bridge, both will have the same lifetime, or the one without the salt bridge? None of the options is not true. So that's just simply added for making it as four options. So among the three, which one is correct? Or does salt bridge does not play any role? That's what is B. So does salt bridge have a role in making the electrochemical cell function for a longer time? We discussed the use of salt bridge as a source for maintaining the charge neutrality in the system, how it actually improves the electrical conductivity or the makes the conductive path, lowers the internal resistance, but does it affect the lifetime of your cell? If yes, then how? Any answers? So the answer is the one with the salt bridge will have a longer function time. But my question is how? Let's end the discussion here for today's session. Anyone who knows how does the salt bridge help in extending the lifetime of a galvanic cell? Because we need to know, right, how it helps. It helps, that's okay, but how it helps. So let me know on this. So I think we can conclude the session for today. Any doubts or anything that you want to discuss, you can let me know. There are two questions, those two questions, and then I'll give a series of other questions. So in the last live interaction session, I thought of giving few of the questions like kind of practice problems, but since we were not very much comfortable with the concept of Nernst equation, I thought that it may not be very much useful apart from the mathematics that you do to solve the problem. So since in this week we know more about Nernst equation and how to apply and use them, and we have solved two or three problems. Apart from the two problems that is already there in the presentation, I will be adding a set of questions, not much but few. So please take it as a practice session anytime during the weekend. If you have anything that you would like to discuss, then we can have a discussion on that in the next live interaction session. So if you have anything to discuss, please let me know. So let me stop sharing. Yeah. So anything that you would like to let me know, any feedback on, or anything that you actually want, or you're expecting me to do related to this course. As I said, it's a very short course for 4 weeks. We are almost 50 percentage of the course is done. So we have two more weeks live interaction session, and then after that we will be done. So in case to if you want to let me know that you want something to add to the presentation, then do let me know, or any feedback that you have for me. Okay, so in case if you have any queries, or if you want to let me know any feedback, then please let us know in the Q&A session of the course page of the NPTEL course page for this particular course on bioelectrochemistry, or you can email me your suggestions and your queries, your doubts also in my email ID. My email ID is available in the presentation that was uploaded in the last week. So please let me know. So let's just conclude the session for today. The video is being recorded and it will be uploaded on YouTube, and then the link will be made available to you. So I hope all of you here know how to access the recordings. So in case if you don't know, then please make a note of it. In the NPTEL announcement page, you in the left hand side bottom, you can see problem solving session Jan to May 2026. If you click on to that link, you will be directed to an Excel sheet where you can access the course, I mean the live interaction sessions recording and the presentations that we are using in these sessions. So I thank everyone for joining today's live interaction session. I thank Professor Mainak Das as well as the NPTEL team for providing me this opportunity to interact with you all in this Saturday afternoon. Our next live interaction session will be on 7th of January, 7th of February, same from 5 p.m. to 7 p.m. So till then, keep learning the course. I hope you are enjoying the course as well. So thank you and have a nice weekend and a week ahead. Thank you and bye.